Somewhere beyond Neptune, 5 times farther than Pluto ever gets, something massive is hiding. Planet 9, a world perhaps 10 times Earth's mass. Never seen. Never photographed. But its gravitational fingerprints are everywhere. Dozens of distant icy objects have orbits that cluster unnaturally in one direction. Despite searching for nearly a decade with the world's most powerful telescopes, despite mapping millions of stars and galaxies in that same patch of sky, we still haven't found it. Here's the paradox: we can predict where a planet should be based on how it tugs on distant rocks, but when we look there, we see nothing. How is it possible to be so close and still miss something the size of Neptune? And how much longer before we finally see it, or prove it was never there at all? The hunt for Planet 9 didn't start with a telescope. It started with a statistical anomaly, and the man who killed Pluto. Mike Brown discovered Eris in 2005, the icy world whose size triggered Pluto's demotion. By 2014, he and Konstantin Batygin were studying a different puzzle: why do the most distant objects in the solar system all tilt the same way? 6 distant icy bodies, Sedna, 2012 VP-113, and others, had orbits that pointed in nearly the same direction. The odds of that happening by chance? About 0.007%. Something was shepherding them. Batygin ran thousands of simulations. Only one scenario fit: a planet roughly 5 to 10 Earth masses, orbiting 400 to 800 times farther from the Sun than we are, on a tilted, elongated path. Here's the counterintuitive part: they predicted Planet 9 before they went looking for it. The math came first. The search came second. Within weeks of publishing their prediction in January 2016, observatories worldwide turned their instruments toward the predicted zone. But there was a problem. Planet 9's most likely position lies near the plane of the Milky Way, one of the densest star fields in the sky. Finding a faint, slow-moving dot among millions of background stars is like spotting a single dark pebble on a gravel road at night. So began the longest, most methodical planet hunt in modern astronomy. In 2016, the prediction was published with an estimated magnitude of 22 to 25, roughly 600 times fainter than Pluto. By 2017, the Subaru telescope in Hawaii began deep surveys of the predicted zone, imaging the same patches of sky months apart to detect motion. In 2019, orbital clustering strengthened. Now a dozen objects showed the pattern. Alternate explanations fell below 0.4% probability. By 2021, new evidence emerged. Planet 9 explained why the solar system's orbital plane is tilted relative to the Sun's spin by 6 degrees. No other model did. In 2023, machine learning algorithms trained on synthetic Planet 9 orbits began scanning archival data, hoping the planet was photographed years ago and overlooked. Tens of thousands of candidate images were flagged, each requiring manual review. But still, no confirmed detection. 2 paths have emerged in the search. Path 1, Planet 9 is real, and we just haven't looked in the right place yet. Supporters point to the clustering of distant orbits, now including 19 objects, the solar system's axial tilt, the existence of orbits perpendicular to the main plane, and the lack of any other explanation that fits all the data. Under this model, Planet 9 is likely near aphelion, its farthest point from the Sun, making it coldest, dimmest, and slowest moving. It could take 10,000 to 20,000 years to complete one orbit. Path 2, there is no planet. The clustering is a statistical mirage caused by observational bias. Skeptics argue we've only found distant objects in certain parts of the sky because that's where we've looked most. Small sample sizes make statistical flukes possible. No direct detection after 9 years suggests the planet may not exist. Some propose alternative explanations: a temporary disk of small icy bodies that has since dispersed, gravitational perturbations from passing stars millions of years ago, or modified gravity at extreme distances. Here's the current status with a counterintuitive comparison. If Planet 9 is near its closest approach, we should have found it by now. But if it's near aphelion, even our best surveys would see it as a magnitude 24 to 25 object, fainter than anything the Hubble Space Telescope can detect in a reasonable exposure time. A magnitude 25 object may not seem like much, but imagine this: you're in Los Angeles looking at a single candle flame in New York City at midnight through fog, and the flame is moving 1 inch per hour. That's the challenge. Each telescope image captures a frozen moment. To detect Planet 9, you need to compare images taken months apart, align them perfectly, subtract the stars, and look for the one that moved. So far, nothing has moved the right way. To understand where Planet 9 is hiding, we need to define two commonly confused terms: the Kuiper Belt and the scattered disk. The Kuiper Belt is like a cosmic junkyard of leftover planet-building material, a relatively flat disk where objects orbit in predictable, mostly circular paths. 30 to 50 Australian dollars from the Sun. Pluto lives here, along with tens of thousands of smaller ice balls. The scattered disk is the frontier. These objects were kicked into wild, elongated orbits, probably by gravitational encounters with Neptune billions of years ago. Their orbits are tilted, stretched, and unpredictable. Some swing out to 1,000 Australian dollars or more. The exact moment of transition happens when an object's closest approach to the Sun is beyond Neptune's gravitational influence, roughly 50 Australian dollars or farther. At that distance, Neptune can't scatter you anymore. You're in the extreme trans-Neptunian object zone. Here's the significance: these objects should be randomly oriented. Gravitational scattering is chaotic. It should spray objects in all directions like a deck of cards tossed in the air. But they're not random. They cluster. The probability of random clustering is less than 0.2%. That clustering is the smoking gun. Now place this in larger context. At 30 to 50 Australian dollars is the Kuiper Belt, reached by New Horizons in 2015. At 50 to 100 Australian dollars, the scattered disk begins, with Sedna's perihelion at 76 Australian dollars. At 150 to 250 Australian dollars is the clustering zone where Planet 9's gravity dominates. At 400 to 800 Australian dollars is Planet 9's predicted current location if near aphelion. At 1,000 to 2,000 Australian dollars is the inner edge of the Oort cloud, the reservoir of distant comets. Planet 9 sits in the gap between the scattered disk and the Oort cloud, a region we've barely begun to map. The timeline to reach these milestones: 9 years for New Horizons to reach Pluto at 33 Australian dollars, about 50 years hypothetically for a direct mission to 400 Australian dollars at New Horizons speed, and about 300 years for sunlight to travel to Planet 9 and back, which is why we're using reflected light, not active radar. We're searching across a distance so vast that light itself becomes slow. Let's restate the core mystery. How do you find a planet you can't see, in a region of space where even sunlight barely reaches? The answer lies in an almost miraculous mechanism: reflected sunlight. Planet 9 doesn't generate its own light. It's a cold, ancient world, perhaps with a thick atmosphere of hydrogen and helium, maybe covered in methane ice. Its only illumination comes from the Sun, a distant, faint pinprick in its sky. Here's a household comparison: imagine holding a basketball in a pitch-black warehouse. Someone a quarter-mile away shines a penlight at it. You're trying to see the basketball by the tiny bit of penlight reflecting off its surface. Now imagine the warehouse is the size of a solar system, and you're looking through a telescope the width of a dinner plate. Let's follow a single photon's journey. Light from the Sun to Earth takes 8 minutes, 20 seconds. Light from the Sun to Neptune takes about 4 hours. Light from the Sun to Planet 9 at $800 takes about 4.5 days, then the same time back to Earth. Total round trip, 9 days. If you took a photo of Planet 9 today, you'd be seeing sunlight that left the Sun over a week ago, bounced off a frozen world, and crawled back to your telescope. Light spreads out as it travels. Brightness falls off as the square of the distance. At Earth, the Sun delivers about 1,300 watts per square meter. At Neptune, that drops to about 1.5 watts per square meter, 900 times dimmer. At Planet 9, the Sun delivers roughly 0.002 watts per square meter, 640,000 times dimmer than at Earth. But it gets worse. That faint light has to reflect off Planet 9, then travel another $800 back to us, losing intensity again by the inverse square law. By the time reflected light from Planet 9 reaches Earth, each square meter of its surface contributes only a handful of photons per second to our telescopes. To gather enough photons to detect Planet 9, you need a truly enormous light bucket. The Subaru telescope in Hawaii has a mirror 8.2 meters across with a light collecting area of about 53 square meters. Even with that massive mirror, Planet 9 would contribute only a few dozen photons per minute, if it's in the field of view, if the atmosphere is stable, if the exposure is long enough. Because Earth rotates, no single telescope can watch the same patch of sky all night, every night. That's why the search requires a coordinated network. Subaru telescope in Hawaii for deep, narrow-field imaging in the northern sky, Pan-STARRS in Hawaii for wide-field survey scanning, Vera Rubin Observatory in Chile, operational in 2025, imaging the entire southern sky every few nights, and DE-CAM in Chile for wide-field infrared imaging to catch Planet 9's faint heat signature. Together, these observatories provide continuous, overlapping coverage of Planet 9's predicted zone. If it's out there, one of them will see it move. Here's the problem: there's no ticking clock on Planet 9 itself. It's not running out of power. But our ability to find it is constrained by time and funding. Telescope time is precious. Observatories receive 5 to 10 times more proposals than they can schedule. Every hour spent searching for Planet 9 is an hour not spent studying distant galaxies, supernovae, or exoplanets. And there's no guarantee Planet 9 is where we think it is, or that it exists at all. So the search proceeds in fits and starts, a few nights per year at each facility, stitching together a mosaic of the sky one pixel at a time. Instead of dedicated Planet 9 missions, astronomers rely on parasitic observations, piggybacking on other surveys. When Pan-STARRS scans for asteroids, it also captures Planet 9's zone. When Vera Rubin maps the Milky Way, it doubles as a Planet 9 search. This leverages existing infrastructure without requiring new funding, but it also means the search is opportunistic, not systematic. In 2016, about 10% of the predicted zone was surveyed to sufficient depth. By 2020, that reached 40%. By 2024, about 60%. By 2025 projected, Vera Rubin comes online, pushing toward 85 to 90% within 3 years. To maximize efficiency, the search has adopted several strategies: machine learning to pre-filter candidates, reducing human review time by 95%, archival mining, scanning old images for missed detections, citizen science projects like Backyard Worlds to crowdsource analysis, and infrared surveys to catch Planet 9's faint thermal glow, not just reflected light. In 2023, the last dedicated Planet 9 search night at Subaru was cancelled due to budget cuts. The final image captured 200 square degrees of sky near the galactic plane, thousands of stars, no planet. The camera logged its observation, saved the data, and moved on to the next project. No fanfare. Just another empty field. Today, the search continues at reduced intensity, a few nights per semester at Subaru, automated scans by Pan-STARRS, and anticipation of Vera Rubin's first light in 2025. If Planet 9 isn't found by 2028 to 2030, funding and enthusiasm may dry up. The hypothesis will remain unresolved, neither proven nor disproven, and future astronomers will need new evidence to justify renewed searches. The Planet 9 search has faced multiple crises. In 2017 came the lost objects crisis. Several key objects used to predict Planet 9's location were discovered years ago with limited observations. Their orbits were based on only a handful of data points. If those orbits were wrong, the entire clustering pattern could be a mirage. Astronomers re-observed these objects with better instruments, refining their orbits to subarcsecond precision. The clustering held. The updated orbits actually strengthened the statistical case for Planet 9. From 2019 to 2021 came the galactic plane contamination crisis. Planet 9's most probable location lies near the galactic plane, where millions of background stars create false positives, objects that appear to move but are actually distant galaxies or binary stars. Researchers developed algorithms to distinguish real solar system motion from parallax shifts, proper motion of background stars, and image artifacts. Every candidate required manual review, tens of thousands of hours of human labor. By 2022, contamination was reduced by 90%, and the false positive rate dropped from about 1,000 per night to fewer than 10. A future problem looms: the faintness limit. If Planet 9 is smaller or more distant than predicted, it could be fainter than magnitude 26, beyond the reach of current ground-based telescopes, even with long exposures. NASA and ESA are considering a dedicated space mission, either a wide-field infrared telescope or a formation of small satellites, to search from above Earth's atmosphere, where thermal background and atmospheric turbulence don't interfere. Such a mission could detect objects 2 to 3 magnitudes fainter than ground-based surveys, extending the search to Planet 9 candidates at $1,000 or beyond. Timeline: earliest launch around 2032 to 2035, if funded. The search for Planet 9 is a marathon, not a sprint. Observatories must balance Planet 9 time with other priorities. Funding is uncertain. The predicted zone is vast. But there's reason for optimism. The Vera Rubin Observatory will begin full operations in 2025. Over the next 10 years, it will survey the entire southern sky every few nights, going deeper than any previous ground-based survey. If Planet 9 exists within the predicted range, Vera Rubin will almost certainly find it by 2030 to 2032. As of 2024, that's 6 to 8 years until a definitive answer. If Planet 9 isn't found by 2032, one of three things is true: it's farther, smaller, or dimmer than predicted, requiring space-based infrared surveys; it's in a part of the sky we haven't searched yet, unlikely given Vera Rubin's coverage; or it doesn't exist. This is not an open-ended search. Within a decade, we'll know. Either we'll have images of a new world, our solar system's ninth planet, lurking in the dark, or we'll have to rewrite the theory and explain the orbital clustering some other way. The clock is ticking. The telescopes are ready. The data is coming. All that's left is to look. The Planet 9 hypothesis was published in January 2016. The original expectation was that it would be found within 5 years. As of 2024, it's been 8 years, and the search continues. When the search began, the best surveys used CCDs with about 1 gigapixel per exposure. Vera Rubin's camera has 3.2 gigapixels, the largest digital camera ever built for astronomy, capturing an area of sky the size of 40 full moons in a single shot. Early surveys processed about 10 terabytes of data per year. Vera Rubin will generate 20 terabytes per night, a 700-fold increase. The objects we're using to infer Planet 9's existence, distant objects like Sedna, were discovered with telescopes and cameras that are now considered obsolete. Yet those faint, ancient worlds are leading us to what could be the most distant planet in our solar system, a giant world that has orbited in darkness for billions of years. Whether or not Planet 9 exists, the search has already transformed our understanding of the outer solar system. We've discovered dozens of new distant objects. We've refined models of planetary formation and migration. We've proven that even in our own cosmic backyard, mysteries remain. And if Planet 9 is out there, it will continue to travel through the dark, patient and unseen, until the moment a photon from our sun bounces off its frozen surface, crosses $800 of empty space, and lands on a sensor in Chile. That moment could be tomorrow, or it could be in 2030. But it's coming. And when it does, we'll finally meet the solar system's hidden giant.